Okay, so we've looked at how to use the substitution rule in integral calculus to solve for indefinite integrals. But what do we do with definite integrals, where you're doing it from a to b, the integral for that particular period? So how is it different? Well, let's dive in and find out. So first of all, remember this? This was the example we used from indefinite integral, except it didn't have this from 0 to 3. It was just an indefinite integral of it. And I think I don't know whether I was being clever or what. I don't know where I got this. It doesn't end up, the answer doesn't end up being particularly neat. So I'm not quite sure where I got these numbers. But anyway, let's go ahead and do it anyway. I've got the PowerPoint, might as well. So we remember how to do the integral of this. Remember, for substitution, we let u equal 1 plus x squared. That meant that du was 2x dx. Great. So we ended up with the square root of u du as the thing that we were going to then integrate. And we did. It was fun. Remember that? But the question is then, what is a and b when you're integrating the square root of u du? Because it's not going to be the same. 0 to 3, that's the x. So you could wait into the end, I suppose. You could wait and, well, no, you can't wait until the end. Anyway, so let's go ahead and think about this, shall we? Here's the key. You ready? And now for the big concept in this video. What's important is we're asking what is u at these points. And it turns out not to be very hard at all to do that, because we said that u was 1 plus x squared, right? So what is u at 0 and what is u at 3? Wow, that's easy. I could have done that way back in high school in algebra, right? So a is going to equal 1 plus 0 squared, which is 1, because 0 squared is 0 and 1 plus 0 is 1. See, this is easy. Wow, it got me all worked up. And then the b is going to do the same thing for 3. So 1 plus 3 squared is 9. 1 plus 9, I can do 1 plus 9 at elementary school, right? It's 10. So basically, we can reformulate this. We already done this, right? That this, using substitution, ends up being the square root of u du. But now we know that instead of it going from x equals 0 to x equals 3, now it's going from a equals 1 to b equals 10. And once we have that solved, it's all easy, except that I picked an example that wasn't neat. What was I thinking? So again, this is the recombobulated substitution form from the integral from 1 to 10 of the square root of u du. So let's go ahead and do u. So remember, when we integrated this, we took it up a power, added 1 to it. 1/2 plus 2 halves is 3 halves. And then we needed a number in front, so it'd cancel out when we did the derivative of it. So 3/2 times 2/3, it disappears, and it's u minus 1 is 1/2. We end up, okay, everything, fundamental theorem of calculus, everything is at peace with the world. Okay, so we already did that in our video on the indefinite integral. But now we're going to plug in from 0 to 1, right? So this is where, what was I thinking? So when we plug in the 10, it's going to be 2/3 10 to the 3/2 power minus 2/3 times 1 to the 3/2 power. Now this part's easy, right? Because 1 to any power is 1, and so we have minus 2/3. The problem is this isn't really reducible. 10 cubed is 1,000, and the square root of 10,000 it's not a neat kind of thing, right? So basically it ends up being, and I factored out the 2/3 because you got 2/3 on both of these, factored out 2/3 times the square root of 10 cubed minus 1. But anyway, I went ahead and I saw it through, right? But it's a bit of a not as nice as a nice one would have been. But that's okay. You got the concept. This has been using the substitution rule with definite integrals. And again, what's the key? The key is that you've got to find out, important, what is u at these points? Because you can't plug in for x. Once you've converted it to a u form using substitution, what is u at the 2 points? Okay, so that's the integrating that. now let's do some final points. Let's throw them in here. Not every version of James Stewart does this in this particular section, but let's go ahead and get it over with. So what is an even function? An even function is where there's symmetry about the y-axis. In other words, where f of minus x is the same as f of x. So if you've got x on this side, minus x is on the opposite side. So basically, however it looks, it's going to be the same on both sides, right? You're going to have symmetry about the y-axis. That's called an even function. So then what is an odd function? Well, they're all odd to me. Okay, mathematically speaking, what's an odd function? An odd function is where f of the opposite of x equals minus f of x. Now think this through. So if you've got an x over here, it's going to be the same as minus x over here. Basically, we're going to have symmetry about the origin. Because if you've got f of x over here, it's going to be minus f of x over here. And if you have, and same thing the other way. So an odd function is one in which there's symmetry about the origin. Psych, you thought it was going to be symmetry about the x-axis, right? No. A even function is symmetry about the y-axis, and then an odd function is symmetry about the origin. So what does that mean with regard to integration? You already knew this probably. For even functions, the integral from minus a to a, it's going to be the same on this side as it is on this side. And so basically, if you went from 0 to a and doubled it, that would be what it was, because it's the same on both sides of the y-axis, right? So we could go from 0 to whatever and double it, and we've got the same thing. So from minus a to a is the same as from 2 times 0 to a. For odd functions, it's going to equal 0, right? Because you're going to have the same amount on top as you have on bottom, or vice versa. So it's going to cancel out, and you're going to end up with 0. So the integral from minus a to a for odd functions is 0. The integral from minus a to a for even functions is twice from 0 to a. And that is the end of 5.5. We have done substitution.